All right, let's go through and look at an example. So what we've seen is that when we have systems of equations, we can find the eigenvalues, and if the real part of every eigenvalue is negative, it's going to be stable, right? If there's no complex valued eigenvalues, there will be no oscillations, and it will decay exponentially to zero, and we're going to call that, oops, not a sink, like the kitchen sink. Okay. If at least one of the eigenvalues has positive real part, then in that case, it's going to grow exponentially. And if there's no complex valued, there'll be no oscillations, and it'll grow unbounded and will be called a source. I gotta be careful. Your authors in your book take a different approach. If all the lambdas are real and positive, then it's called a sink. Otherwise, it's called a saddle. You've got to be careful on that. And that's going to be true with the homework. All right, so let's look at some examples. Suppose we have the system of differential equations. They're in this form, and k is a parameter. And the question is, what happens for various values of k? So for any given value of k, we would like to just make a rule up that'll tell us exactly what to expect. Will it grow? Will it decay? Will it oscillate? Will it be a sink or source? What's going on with that? Okay, so at the end, I should have basically a table that I can just look at my value of k and say it's in a given range, and then explain what's going to happen. Okay, and the key thing here is all I need to know is about the eigenvalues. So if I take my matrix, I subtract lambda from the diagonals, and take the determinant, set that equal to 0, that's going to tell me the values of lambda. This is a 2x2 system. By the way, that immediately tells us that our x looks like x and y. It's two unknowns. So I'm going to multiply the diagonals. So I'll get a minus lambda from there times k minus lambda minus 3 times 1. So let's clean that up. If I multiply through by the lambda, I get minus lambda k plus lambda squared minus 3. Let me rewrite that. Oops. So I get lambda squared plus k times lambda. Oops, I gotta be careful. It's lambda squared. That should be a minus. Minus 3 is 0. Is that correct? So lambda squared minus k lambda minus 3 is 0. And since I don't know what k is, I can't factor this. So I'm just going to go straight for quadratic equation. So my b is minus k. Minus a minus k is k, plus or minus. Then my b squared minus 4. Coefficient of lambda squared is 1. A is minus 3. All over 2 times 1. All right, so let's clean that up. So that becomes k plus or minus k squared plus 12 all over 2. So I have two eigenvalues. One is going to be 1/2 of k plus square root of k squared plus 12. And the other is going to be 1/2 of k minus the square root of k squared plus 12. And by the way, I'm assuming k is a real number, and it's any real number. So it could be positive, negative, whatever. This is the full possibilities for k. So you should stop and just ask, how does this feel? Notice that this is always, square root's always going to be positive. And since I take k squared plus 12, this is always going to be bigger than k. So even if k is negative, I'm going to add something bigger than its absolute value. So this is always going to be positive. So this is going to be unstable no matter what I use for k. Additionally, it's either going to be a source or a saddle. Right? And it's only going to be a saddle if this is negative, and if this is positive, it's going to be, then it has to be a source. So the question is what's going on here. Notice if k is negative, I'm going to subtract something, and then it's going to be negative. So I think if k is negative, lambda 2 is going to be negative. And if k is positive, notice again, k squared plus 12 is going to be bigger than k in absolute value. So if I take k and it's positive and I subtract something bigger, it's going to be negative. So I think this is going to be a saddle no matter what I do. So let's see. How do we show that? So where were we? We had this system of equations. And we have two eigenvalues. Lambda 1 is 1/2 k plus square root of k squared plus 12. Lambda 2 is 1/2 k minus square root of k squared plus 12. And this is really sloppy. Sorry, this is k. Okay. So let's look at k plus square root of k squared plus 12 all times 1/2. So I think that's got to be positive no matter what. So let's see if that's true. So I can multiply both sides by 2. So I think that's true. If I subtract k from both sides, I get k squared plus 12 is greater than or equal to minus k. Now, the thing on the left has to be positive. So if k is greater than 0, that's true. Okay, so if k is greater than 0, that means lambda 1 is positive. If k is negative, then I have to ask, what does this imply? Is this still true? So let's see. If I square both sides, then it should still be greater than, right? If I take a bigger number and square it, it's going to be bigger. And I got to be careful. If k is negative, the thing on the right is positive. So what I'm doing is okay. So square root of k squared plus 12 squared is k squared plus 12. And then minus k squared is k squared. And this says that 12 is greater than 0. So that's true. So this means that lambda 1 is always positive for all k. Now let's look at our lambda 2. Our lambda 2 now was 1/2 k minus square root of k squared plus 12. And the claim is this has to be negative, right? That was our feelings about what we think is going to be true. And now I have to verify if my reasoning was correct. So I have 1/2 of k minus the square root of k squared plus 12, I think is negative. I think it's true for all k, I'm not sure. So I multiply both sides by 2. And I get 0 on the right. Let me add k squared plus 12 to both sides. And the question is this true? So first of all, if k is less than 0, then the thing on the left is negative and the thing on the right is positive, and it's true. All right, so that means in this case, my lambda 2 is negative. If k is greater than 0, what does this imply? Well, the thing on the left is positive and the thing on the right is positive, so I can square things and I don't have to worry about signs flipping. So if I square both sides, I get a k squared plus 12 on the right, subtract k squared from both sides, get 12 is greater than 0, which I believe is true. So that means my original assumption was true. So what do I have? I have my lambda 1 is greater than 0 for all values of k, and my lambda 2 is negative for all k. So this, my stability is going to be unstable, and it's going to be a saddle for all possible values of k. All right, let's look at another example. Let's suppose we've got a system. So the derivative of my state is equal to 2, 1 plus k, 3 plus k, x. So I immediately see, since this is a 2 by 2 matrix, my x has two variables, x and y. And I'm going to do exactly what I did before. I'm just going to find the eigenvalues. And depending on the values of the eigenvalues, that's going to tell me if it's stable or unstable, whether or not I have oscillations. And I'm going to assume k could be any possible numbers. So again, my goal here is to tell you the stability if you give me any value for k. So at the end, I should have a table that says if k, you give me the value of k, I can look straight in the table, tell you exactly what's going on with the stability. So I subtract lambda from all the diagonals, take the determinant, set it equal to 0. So this is going to be a bit of a mess. So I get 2 minus lambda times 3 plus k minus lambda minus 2 times 1 plus k. So I'm going to expand it out as far as I can and then see what happens. So let's see, 2 times 3 is 6. 2 times k is 2k. 2 times minus lambda is minus 2 lambda. Now I deal with this. Minus lambda times 3 is minus 3 lambda. Minus lambda times k is minus lambda k. And then minus lambda times minus lambda is lambda squared. Multiplying that through, I get minus 2 minus 2k. So let's collect all the like terms. I've only got one lambda squared. For my lambda terms, I've got minus 2 lambda minus 3 lambda minus lambda k. So this is minus 5 plus lambda k. Oops. Sorry, that's not right. This is going to be minus 5 plus k lambda, right? Because that's going to be minus 5 lambda, and that's going to be a lambda k, and I factor out the minus. Okay. That was harder. Made that harder than it needed to be. Then I'm going to have 6 plus 2k. So 6 minus 2 is 4. Plus 2k minus 2k is 0. So let me rewrite that. So it's... Let me try again. 0 equals lambda squared minus the quantity 5 plus k lambda plus 4. All right. So I've got to solve that for lambda again. I don't know what k is, so I'm not going to mess around. My lambda then is going to look like minus b. So b is minus 5 plus k. So minus a minus 5 plus k is 5 plus k. Then plus or minus minus 5 plus k squared minus 4 times 4 times 1 all over 2 times 1. So that's a right mess. So minus 5 plus k squared is the same thing as 5 plus k squared minus 4 times 4, so minus 16 all divided by 2. And I want to keep it like this because it's going to be easier to do algebra because those two things are the same. It's going to make it easier to think about. So we started with this differential equation, 2, 1 plus k, 3 plus k x, and we had lambda 1 is 1/2 of 5 plus k plus the square root 5 plus k squared minus 16. And lambda 2 is going to be the same thing, but I'm going to subtract the square root of 5 plus k squared minus 16. All right, so now I need to ask what's going on with this in terms of my stability. So what could happen? I could get the thing in the square roots is negative. If that's the case, I'm going to get oscillations, and the only real part is 5 plus k, and I think that's going to be straightforward to deal with. If they're both real, that's going to be a mess. So let me do the easier thing first. So the first case is it's complex valued, which means that the 5 plus k squared minus 16 is negative. Okay? If that's the case, then lambda 1 is going to be 1/2 5 plus k. And now if I factor out an I, I'm going to flip the sign here. This becomes 16 minus 5 plus k squared. And lambda 2 is going to be the same thing, only I'm going to subtract the square root of 16 minus 5 plus k squared. Right, so if this is negative, I pull out a negative 1, which flips the signs, and then I'm going to factor out the square root of minus 1, which is the I. So this is complex, and this is the imaginary part. That's the imaginary part. So we're going to get oscillations. And the real part, notice the real part is the same in both cases, is 1/2 of 5 plus k. So if 1/2 of 5 plus k is negative, it's going to be stable. So multiply both sides by 2, so I get 5 plus k is less than 0, so k is less than minus 5. All right, so if this is the case, it's going to be stable. Likewise, if I have 1/2 of 5 plus k is greater than 0, it's going to be unstable. So that multiply both sides by 2. So I get 5 plus k is greater than 0, k is greater than minus 5. Now I need to be a little careful here because I'm saying this is true and this is true. So I have to ask under what circumstances is this true and this is true, and I have to do the same thing for that. So again, what was our differential equation? 2, 1 plus 3, 1 plus k, 3 plus k, x. We're looking at the complex cases, so we know that 5 plus k squared minus 16 is negative, and for the stable case, k is less than negative 5. For the unstable case, k is greater than minus 5. And we call this case 1 and this case 2. So for 1, k is less than minus 5, and 5 plus k squared minus 16 is negative. So what am I dealing with here? I have for k, there's the k 0, so I'm focused on minus 5. So I'm looking at this case where it's negative and less than negative 5. So I got to deal with what does it mean for 5 plus k squared to be less than 16. In order for, so think of this as y equals x squared. If I'm squaring something and it's less than 16, so that's going to happen at minus 4 and 4. For this thing to be less than there, I have to be less than 16. I have to be between minus 4 and 4. Right? So if I square root both sides, this thing quantity squared can be less than 16 if the thing inside is between plus or minus 4. By the way, this is true regardless of the k less than minus 5, so I'm going to reuse this later. So if I subtract 5 from both sides, I get minus 9 is less than k is less than minus 1. So my condition that it be complex, that 5 plus k squared minus 16 be less than 0, implies that k is between minus 9 and minus 1. So that's going to happen for k between minus 9 and minus 1. And for both of these things to be true means that k has to be between minus 9 and minus 5. Likewise, for the second case, where k is greater than minus 5, everything I just did is still true because I'm still working with a complex case. So I know that k is between minus 9 and minus 1 from here. So what does that mean? So k is greater than minus 5 means that I'm out here somewhere. K is between minus 9 and minus 1 means I'm in here. So this is true if k is between minus 5 and minus 1. Okay, so what do we have at this point? We have the ODE system is still the same. We have the complex case that if k is between minus 9 and minus 5, we have oscillations and it's stable. And if k is between minus 5 and minus 1, we have oscillations and unstable. Now we're going to deal with the real valued case. And we already know this is going to be tricky. So what did we have? We had, let's go back. This is our lambda 1 and lambda 2. So let's rewrite that. Lambda 1 is 1/2 5 plus k plus the square root of 5 plus k squared minus 16. Lambda is 1/2 5 plus k plus the square root of 5 plus k squared minus 16. We know that since it's real valued, that 5 plus k squared minus 16 has to be positive. And we already saw in the previous case that being able to work with this and knowing what that means is going to be really important. So let's just go ahead and do that now because we know we're going to use it later. Let me add 16 to both sides. So I have something squared is bigger than 16. How can that happen? So there's my 16. I am looking for, and this is going to be between 4 and minus 4. Between minus 4 and 4, x squared falls below 16. But if I'm less than minus 4, I'm above 16. And if I'm greater than 4, I'm above 16. So this implies that either 5 plus k is greater than 4 or 5 plus k is less than minus 4. Right? And so now taking this expression, k has to be greater than minus 1, and this one says that k is going to be less than minus 9. And that makes sense because what we already found out that from here, from minus 1 to minus 5, and here it's going to be stable and oscillate. And then, nope, I'm sorry, that is, sorry, minus 5 to 1 is unstable. Need to be more careful. From minus 9 to minus 5, this is stable and oscillates. And what we just found out now is that we are looking for k greater than minus 1, which is out here, and then k is less than minus 9, which is out there. And if we're lucky, we'll have consistent results here. So just guessing, since this is unstable here, I'm going to guess that's probably going to be unstable, and that's going to probably be stable. But this being unstable, this could be a source, but it could also be a saddle. I don't know. If it's stable, that means both eigenvalues have to be negative. So I think here is going to be less complicated. So I'm going to do that first. All right. So my eigenvalues, I said one was square root of 5 plus k plus the square root of 5 plus k squared minus 16. And the other one is 5 plus k, minus the square root of 5 plus k squared minus 16. Now notice, anytime you take the square root of something, it has to be positive by definition. So for my lambda 1, this could be positive or negative, I don't know. But whatever it is, I'm taking it and I'm adding something positive. And here I take the same thing and I subtract something positive. So I know that lambda 2 is less than lambda 1, just by the way I wrote this. Okay. So what could happen? I could have, well, let's just focus on my two cases. I said that, lambda is less than minus 9. Sorry, not lambda. K is less than minus 9, and I want to know, what does this imply? Notice, I think it's going to be stable, which means that lambda 1's got to be negative. If lambda 1 is negative, lambda 2 has to be negative. So if I can show that lambda 1 is negative, I'm done. So is this true? I think this is true. So what I have 1/2 5 plus k plus the square root of 5 plus k squared minus 16. Right, so I know right now that 5 plus k squared has to be greater than 16 because I know that my k is less than minus 9. And I got that from making that true. So that means, and we already said that means that the 5 plus k is either greater than 4 or the 5 plus k is less than minus 9. Minus 4. But since I already said k is less than minus 9, I know, right, k is less than minus 9 comes from that right there. So that means my 5 plus k has to be less than minus 4. Okay, so this thing, 5 plus k squared, has to be bigger than 16, right? But it's going to be, because I'm taking 5 plus k, squaring it and then subtracting, once I take the square root, this whole thing has to be less than 5 plus k in absolute value. So if I take 5 plus k, which I know is going to be negative, and I add something smaller, something positive but smaller in absolute value, this result I think has to be negative. Okay, so that's this second line of reasoning here, and I think that's the one that's going to hold. So let's just see if this is true. I'm going to just assume it. I don't know if this is true, but if I go through and do the algebra and work it out and I get something that's undeniably true, I can basically do everything backwards and show that this statement is true. So I can multiply everything by 2. So I get 5 plus k plus the square root of 5 plus k squared minus 16 is less than 0. All right, so this is positive. I want to work with positive things because then when I square them, I don't get weird negative positive issues. So let me subtract 5 plus k from both sides. Okay, again, I know k is less than minus 9. That's my assumption. If k is less than minus 9, 5 plus k is negative, minus that is positive. So this whole thing is positive. So if I square both sides, I don't have to worry about anything flipping here. So if I square both sides, the square root goes away. And if I square that, I'm going to get 5 plus k squared, and the minus 1 squared goes away. But notice I can subtract that from both sides, and I get minus 16 is less than 0. I believe that. I think that's true. So this implies this, which implies this, which goes all the way up, and that immediately implies, right, this thing right here means that my lambda 1 is negative. And because of this expression here, that means lambda 2 is negative. So this is going to be a stable sink since they're both real and both negative. Boy, okay, let's just recap that. So again, my lambda 1 is 1/2 5 plus k plus the square root of 5 plus k squared minus 16. Lambda 2 is 1/2 5 plus k minus the square root of 5 plus k quantity squared minus 16. And the way I've constructed this, lambda 2 is less than lambda 1. And I've already shown that if I go from minus 1 to minus 5, this is unstable and oscillates. As I go from minus 9 to minus 5, it's stable and it oscillates. And then we just showed that for less than minus 9, it's stable. Both eigenvalues are negative, so it's a sink. The only question now is what's going on for k greater than minus 1. Okay? And where did the k greater than minus 1 came from? This came from a long time ago. Can I find it? Yeah. This came from this discussion. We assumed things were real valued. If that's the case, we know that the thing in the square root has to be positive, which means that either k is greater than minus 1 or k is less than minus 9. So we just showed this case. We've already got those. So let's assume k is greater than minus 1 and ask what does that imply. And we're hoping that we get something consistent. If not, we may have to break this part into 2 pieces, or 3, depending. So we don't know how this is going to come out just yet. So k is greater than minus 1. This is going to imply that 5 plus k squared minus 16 is real, which means that 5 plus k squared minus 16 is greater than 0. What do I know about 5 plus k? Well, if k is greater than minus 1, the smallest this can be is 4. So 5 plus k has to be greater than 4, right? And that's consistent with that. So that means my 5 plus k is positive. And I'm going to, again, for the same reasoning before, I'm going to subtract something whose absolute value is smaller than 5 plus k. So I think lambda 2 is going to be positive. So because of this relationship right now, if I show you that lambda 2 is positive, that means lambda 1 is going to be positive, and then I'll be done. I don't know if that's true yet, but I think lambda 2 has to be positive. If I show this, lambda 1 has to be positive because I'm just adding stuff, and I'll be good. So is this true? Is my intuition correct? So let's just find out. Note that's positive. So I'm going to basically do the algebra, and if I can boil this down to something that's true, that I know is true, then I can basically do all the algebra backwards. So let's multiply both sides by 2. So I get that term is greater than 0. This thing is positive, so let me add it to both sides. And the reason I'm choosing that is because now the left is positive, the right is positive, and if I square it, I don't have to worry about flipping signs for this thing because of those weird negative things. So now if I square both sides, I get on the left 5 plus k squared. And if I square the right-hand side, the square root goes away. Now I can subtract off 5 plus k squared from both sides, and I get 0 is greater than minus 16. I believe that's true. So since this is true, that means this is true, which means this is true. And indeed, lambda 2 is greater than 0. And if lambda 2 is greater than 0 because of that, lambda 1 has to be even bigger. So it's positive. So in this case, both eigenvalues are real. They're positive. It's going to be unstable. And it's going to be a source. Oy, oy, oy. Okay. I'm almost done. My original differential equation was derivative of x is equal to the matrix 2, 2, 1 plus k, 3 plus kx. And I wanted to know what's up with the stability of this for different values of k. And we found that there's 4 cases. From minus 1 to minus 5, it's unstable. It oscillates. From minus 9 to minus 5, it's stable. Oscillates. Out here, it's going to be a stable sink. And out here, it's going to be a stable source. So what does that mean? That means that if k is less than minus 9, it's a stable sink. If I'm between minus 9 and minus 5, it's going to oscillate and be stable. If it's between minus 5 and minus 1, it's going to oscillate and be unstable. And if k is greater than minus 1, it's going to be unstable and a source. And I need this table, and the reason I need this table is you give me any value for k, I can immediately look up where it falls and then tell you what's going to happen with it.